Hello dear students, welcome to lecture 4 on benzene and aromaticity. So in this lecture we will study about what are aromatic compounds, what is aromaticity, how to identify whether a given compound is aromatic or not, and how to understand their stability and reactivity. So let us start this journey with the composition of organic compounds. So historically, organic um, compounds which had characteristic fragrances were called aromatic. And later on, these compounds were found to have unexpected properties, and they were like, for example, they were found to have low H by C ratios compared to aliphatic compounds. That is, the number of hydrogens divided by the number of carbon atoms in these compounds were found to be low. So, this is what it means. For example, a pleasant smelling compound isolated from cinnamon bark known as cinnamaldehyde has a chemical C9H8O, while the 9 carbon containing aliphatic compound with one oxygen, that is C9H20O, has a higher percentage of hydrogen atoms. So these are the structures that you can see, and if you calculate the H by C ratio for these, for one nonanol, that is the aliphatic compound, we have 20 hydrogens divided by 9 carbon atoms, you get 2.22, while for cinnamaldehyde, which has 8 hydrogens divided by 9 carbons, you will get 0.89. So it is quite apparent that aliphatic compounds tend to have high H by C ratios than the corresponding compounds with aromatic fragrances. Thus, these compounds are expected to have a lot of unsaturation. That means they are expected to have many double bonds present, carbon-carbon double bonds present in them. Now, let us move on how we can use this information to predict something about their reaction. Now, as we have seen in the analysis on the last slide, that aromatic compounds have many double bonds. Therefore, you would like to expect reactions typical of a compound containing double bonds, that is alkenes. They have carbon-carbon double bonds. So whatever the reactions about alkenes that we have studied in the last semester, we would naturally expect aromatic compounds to undergo those similar reactions. So here is an assignment question for you. Calculate the H by C ratios for benzene, cyclohexane and cyclohexene. I hope you know their structures. If not, they will be available on the screen for you soon. So benzene has C6H6 and has a low H by C ratios and is expected to have double bonds. You expect it to have undergo typical reactions of alkenes, that is addition reactions, but it is found that experimentally it doesn't undergo addition reactions. Instead, it undergoes substitution reactions. So let us look at this once again. So here is a cyclohexene compound which has a double bond in it. So like all alkenes, it undergoes addition of H2SO4, addition of Br2, and oxidation by KMnO4. These are the typical reactions of compounds containing double bonds, that is alkenes. But if you try to do the same thing with benzene, we find that it doesn't react with H2SO4, it doesn't readily react with bromine, and also it doesn't readily react with the KMnO4 and doesn't get oxidized very easily. But instead, if you treat benzene with bromine along with a catalyst, ferric chloride, then you find that instead of adding the bromine molecule as it does here, it replaces one of the hydrogens and replaces it by bromine atom. Similarly, when you treat benzene with H2SO4 and heat it, you find that instead of the addition product, you end up getting the benzene sulfonic acid. That is, one hydrogen has been substituted by the SO3H group. So why this could be? So this means that benzene has a structure that is unusually stable towards addition reactions. So what this structure might be? So for many years, scientists were wondering, and they proposed many different structures. And one thing is quite obvious, that the H by C ratio suggests that benzene should have 3 double bonds. So if you want to convince yourself with this, please try at your home. And also we will try to do this exercise of calculating the H by C ratios during our class time, and try to convince ourselves that it has 3, it should have indeed 3 double bonds. After much scientific debate, scientists over the years have settled on these two structures. Both of them contain alternating double and single bonds, but neither of them is benzene. So structure 1 contributes equally and structure 2 also contributes equally to the hybrid of the actual structure of benzene. So in other words, benzene is known to be a hybrid of structure 1 and 2, in which 1 and 2 make equal contribution, and therefore you find that benzene does not contain alternating single and double bond. Instead it has all carbon carbon bond distances equal to 1.4 angstrom, which is in between a single and a double bond length. This is due to the presence of resonance in the ring, and a typical cyclohexatriene molecule does not exist, and therefore it is hypothetical, and such a hypothetical compound would have alternating single and double bonds between carbon atoms. So what is this evidence for aromaticity and thermodynamic stability of the benzene? So one fact is well known, that when double bonds are reduced, heat is liberated, that is known as heat of hydrogenation. So let us take this example in which you have 1, 2, 3, 4, 5 and 6. 3N hexene, when it is reduced in the presence of hydrogen and palladium carbon, you get hexane, and heat is liberated in this reaction. So let us apply this knowledge to cyclohexene, which we know has one double bond, and reduction to cyclohexane should release heat as heat of hydrogenation, and experimentally it is found that it releases 28.6 kilocalories per mole. For cyclohexadiene, which is known to have two double bonds, we expect that the heat of hydrogenation should be twice because it has two double bonds, and therefore our prediction says that it should have 57.2 kilocalories per mole. And for benzene, which could also be called as a cyclohexatriene, we expect that if it is having three double bonds, it will have heat of hydrogenation equivalent to 85.8 kilocalories per mole. Please try to remember these numbers. We will need them in the next slide. So what are the experimental facts about these heats of hydrogenation? Cyclohexadiene releases a heat of hydrogenation of 55.2. That means it has 2 kilocalories per mole less energy than we would expect. We were expecting 57.2, but we actually are getting 55.2. It is 2 kilocalories more stable than we were expecting. Then benzene, actually, when you do this same hydrogenation reaction with benzene, it actually releases significantly lesser energy, only 49.8 kilocalories per mole, and therefore it is extraordinarily stable. It is stable by 36 kilocalories per mole. We were expecting 85.8 kilocalories to be released when you hydrogenate benzene, but actually you get 49. So when you get less energy, that means there was less energy available in the first place in that molecule. When its original energy level is low, that means it is stable. So this same argument is depicted here in a nice picture, where this is your expected energy level of the cyclohexatriene, and these are the expected energy levels for the cyclohexadiene, and these are the actual energies for the benzene and cyclohexene. This elegantly explains why benzene is thermodynamically more stable than cyclohexatriene. Now, aromaticity, Huckel's rule. Let us try to understand what is this Huckel's rule. Discovery of the benzenes, scientists were more interested in other aromatic compounds which not only have fragrance but have this additional property of having unusual stability. Therefore, they found that there are many criterias which an aromatic compound generally meets, and one of these is like compounds like benzene have a conjugated carbon-carbon double bond system in a ring. The next criteria is that they are more stable compared to the unconjugated system of similar size. That if you have a compound containing similar number of carbons, they are more stable than those unconjugated systems. And the next criteria is that they are resistant to addition reactions, and instead they undergo substitution reactions. Huckel found that such compounds which satisfy all the A, B and C conditions also have another unique property, and this unique property is that they have 4n plus 2 pi electrons in the conjugated ring, where n could be any integer 1, 2, 3, etc. Hence, the following molecules or species are considered aromatic, because in addition to the A, B, C, they satisfy this criteria that they have, if you count their pi electrons in the ring system, they will satisfy this equation, that is 4n plus 2. So let us take a look at this. Benzene we know is aromatic because it has 4n plus 2, that is 6 pi electrons in the ring. Furan, if you count 2 from this double bond, 2 from this double bond, and 1 lone pair from this oxygen atom, will constitute the conjugated ring system, and that 6 also satisfies the equation 4n plus 2. Therefore, furan and similarly pyrrole and thiopene can also be declared as aromatic. Now let us take a look at this cyclopentadienyl anion. This can be generated by abstracting a proton which was present here. So you remove that proton, leaving a charge behind, thus it is known as cyclopentadienyl anion. So if you count electrons in these rings, 2 from here, 2 from here, and another 2 from here, makes it 6. So again, this seemingly unstable anionic species also satisfies the 4n plus 2 rule and is indeed aromatic. But on the other hand, molecules or species which do contain, instead of the 4n plus 2, if they have 4n electrons only, where n is again the same integers, these compounds are anti-aromatic. That is, they have almost the opposite of all those properties that we have studied about the aromatic compounds. And here are some of the examples. These anti-aromatic compounds are less stable, they are very reactive, and they have very large heats of hydrogenation because they contain the extra energy which makes them unstable. So cyclobutadiene, if you count, is 4, where N is 1, and cyclooctatetraene is having 8 electrons, therefore it satisfies this condition for N, where N is 2. And similarly, you will find that when N is 1, you will get the cyclopentadienyl cation, which has this positive charge and only 4 electrons in the ring. Therefore, this is a highly unstable species and it is in fact anti-aromatic. So I am giving you this assignment to guess which of the following compounds are aromatic and anti-aromatic. Please take a closer look at their structure. Try to count the number of electrons in the ring and check if they satisfy the 4n plus 2 rule or not. Some of these compounds were recently reported in one of our papers. So if you are more interested to know about aromaticity and aromatic compounds and other criteria of determining aromaticity, you can have a look at this reference. So I will see you in the next lecture.